I hope everyone's doing well. I'm Strish. Thank you for joining me for this video where we are looking at something fun. We have over here second order partial derivatives. If z represents a function and assume everything here with regards to z is a function, you have x and y, but here x and y represent independent variables. We can easily determine a second order partial derivative of z. And there are a number of different types of second order partial derivatives. We will look at all of that here by means of a good example. Look over here at this representation. I'm looking here at a second order derivative with respect to the x variable, and you can easily represent this in a way as this. You have that and you have x comma y. Look, I have two x's over here and I'm going to write them out for you, meaning I'm doing the derivative with respect to the x variable twice from that original function z. Look right here at this other representation with regards to now the y variable, where the y second order derivative is being done. Here you can represent it as this. You have two y's coming through over here, two derivatives of y and then the function z. But there is another unique feature of partial derivatives with regards to their second order. It's this. You can also represent something like this. You have over here now a certain other feature coming through. Look at the difference between what you see over here and what you see over here. Here you're still doing a second order derivative, a partial derivative of your function z, but look at the order that's coming through. You're going to do the x derivative first, followed by the y derivative with respect to the x and the y variables which are at play. Now look here at this last representation. You have this. Now the y variable first and then the x, partial derivatives of the y and then the x. Here you can represent it as fyx. The y derivative will be done first, then followed by the x. It's still the second order because you're doing two derivatives of z. And then you know you have x and then y, the variables which are involved. You have to keep these in mind. You have one form right here, another form here, another form right here, and a last form here. The most important or interesting aspect of these second order partial derivatives is if this right here is continuous function, and the partial derivatives, which are indeed functions on their own right or respect, they are continuous as well. If this is continuous, the partial derivatives are continuous, then this right here, these two representations c and d, order does not matter, they should be equal. Whether you do the x derivative first followed by the y, or you do the y derivative followed by the x, the end result of the outcome should still be the same if everything you're looking here at and everything that's coming out in terms of the end product, it's continuous. This will come into play. This representation will be equal to the other representation. We can write it in a better way, in the following way, so it doesn't seem confusing what c and d is. We can say this. You are looking here at a second order partial derivative where the x partial derivative was done before then the y. It should be the same thing as if the y partial derivative was done before the x. Now it makes more sense. These should come through and they should be equal to each other if everything involved is continuous. Let's look here at an example. Our example will arise from this z, which we will call a function 2x squared minus 5xy plus y squared. Assume everything you see with regards to z is a function. Our first task here is to do this right here, second order partial derivative. What we will do here with respect to the x variable, that's what we're doing. You can look at this in the following way. You're doing a derivative with respect to the x variable, but you're doing it twice. And you can see the x's are coming through. Two derivatives with respect to the x variable, and it's not hard because we're looking here at polynomial style of items. The derivative with respect to the x variable from 2x squared, you know you're having a 4x. The derivative of the other item is always treated as a constant. You remember that. You're doing 1, you treat everything else as a constant. Derivative of a constant is a 0. Minus 5xy will be here a minus 5y. This right here is your first order partial derivative. If we do the derivative once more, and we can just say it as this, we have here the partial order derivative of x variable. You know your end result here will be 4 and it should be correct. When you're looking at this z function right here, x squared minus 5xy plus y squared, the second order partial derivative with respect to the x variable should be 4. It will be correct. Now we've done a change. We're looking here with regards to the y variable. The x will be treated as a constant. We're looking here in terms of this representation we have, and then you're gonna look at it as that. You understand this right here is your del symbol, del, and it represents a partial order derivative. There's another name for it, but this right here is the common name, del. It's called a del. It's a partial derivative symbol. When we're looking here at this, the x is your constant, y is your variable to be differentiated. This here is a 0. From here we'll have a minus 5x plus 2y. We'll do the derivative once more. We can represent it as this. And what will we have? We'll do the derivative with respect to the y. This here is a 0. Our answer here should be 2 and it will be correct. Now look right over here. We're doing second order derivative, but we're doing in two different orders. We're looking at two different variables, x and y. X will be differentiated first, y will be as a constant, then y will be differentiated secondly, and then the x will be a constant. You know this right here is your representation as this, as I showed you earlier on, which you can represent in a different way, and I'll show it to you right here. You can look at it as this. You're looking at the x derivative first, followed by the y derivative. As you can see, the x being derived first, differentiated first, followed by the y. And let's do it. This here is our function. When I'm doing the x order derivative, you know this right here is a 4x. Everything else is treated as a constant, but from here I'm getting a minus 5y. This right here is the end result of my just this part right over here, where the x was differentiated first. Now we're looking at this part, and I'm going to do the derivative of this, the partial derivative. X will be a constant, y will be your variable, and you know your answer here will be a minus 5. It should be correct. We end right here with this. We're looking at a second order partial derivative, but the y is being differentiated first, then the x. You know in terms of representation, we're looking at the y derivative first, then the x partial derivatives, and then everything with regards to a function which has the x and the y variables. But in the other way, you can also look at it like this. You're doing the derivative with respect to the y, then you're doing the derivative with respect to the x. That's what we have. Now we're going to look at this part first. We'll do the y derivative first. Here's our function. Treat x as a constant. This is a 0. From here I'm getting a minus 5x. From here I'm getting a plus 2y. Now we look at this other, the second order derivative, but with respect to the x variable, the y will be a constant. This zeroes out. From here I just have a minus 5 and it will be correct. And you will have remembered that the previous answer was also a minus 5. You know now, when your function is continuous, the partial order derivatives are continuous, your second order partial derivatives with respect to this should be equal. Look at the representation I'm showing you. fxy should be equal to fyx. The derivative with respect to x followed by y, it should be equal to derivative with respect to y followed by x. You can formally represent the terminology as this. You're looking at the second order partial derivative where the x partial derivative was done before the y. It should be equal to the second order partial derivative where the y partial order derivative was done before the x. But that is true. As you've seen, we had minus 5 in both cases. When the function is continuous, the partial order derivatives are continuous, this representation or this statement will prove to be true. And that right there is the end of this video. Thank you for watching.